Good afternoon, friends.
Good afternoon, sir.
I shared my screen. Is it visible to you?
Yes, sir.
Okay, fine. So let us begin our discussion with the same circuit which we have seen yesterday, and today we'll see how to perform its simulation practical. Okay. So what we have seen that if this is the RLC circuit given to you, voltage was not applied. This is the series RLC circuit having resistance R, inductance L and C in series, and this switch was open for infinite amount of time. That means this voltage source was disconnected from this RLC circuit for a long time, and at time t equal to 0, we are pressing this switch, we are turning this switch on so that this voltage source will be connected to this RLC circuit. Then by drawing the equivalent circuit at time t equal to 0, we can apply KVL for that particular circuit, and after applying KVL, we can get the second order differential equation, and the solution of that second order differential equation, we have seen that there are having total 4 cases. Case number 1, that is whenever R by 2L square is greater than 1 upon LC. That is, if the values of R, L and C are such that this R by 2L bracket square is far greater than 1 over LC. Then this is case number 1. It gives the overdamped response, and the response of the system is like this. This is the final steady state value V, and this final steady state value it will achieve after a long time this. Okay, so that is the overdamped response. Now if you are making it as case number 2, that is R by 2L whole square, if this value is equal to 1 over LC, then this becomes case number 2, which is the critically damped response. And critically damped response is this. What is the difference in overdamped and critically damped? In critically damped, the final value is achieved earlier than that of in overdamped response. So in overdamped response, the final value is reached somewhere here, whereas in critically damped system, it is achieved somewhere here. So on time axis, it is earlier. So that's why case 2 is better than case 1. Now case 3 is whenever R by 2L whole square, this value is less than 1 over LC, then the system gives underdamped response. That is such sort of response it gives. That means the final value is achieved by the system more earlier than the critically damped response. In overdamped response, that final value was achieved at this particular time. In critically damped response, final value was achieved at this particular time. So it is earlier than the previous one. And in underdamped system, it is achieved at this particular time. So it is again earlier than the previous one. Okay, so underdamped response, it gives the maximum value or the final value or steady state value in earliest time than overdamped or critically damped system or undamped even. Okay, so but in this system underdamped response, there are certain oscillations takes place, and these oscillations are of dying out nature. That means the magnitude of this particular oscillation is the highest, then this, then this, then this, then this, and the oscillations will die out or the response will settle down after certain amount of time, and after settling down, the system will give the steady state value. So these are the three cases which you can see. And the fourth case in which R is 0, that is damping is 0. If damping is 0, then the system will never attain the final value. That means it will only oscillate between the maximum value and minimum value. So it will be a sinusoidal curve which will be observed between this maximum value and this 0 value. Okay. So practically how it will look like. So this is the overdamped response of RLC circuit. So this is the RLC circuit. This 9 ohm is value of R. This capacitor value is 500 millifarad and inductor value is 5 Henry. So this is the RLC circuit, and this path of 2 ohm, it is provided for the discharging. Now case 1, which is overdamped response of RLC circuit, that means value of R by 2L whole square, it is greater than 1 over LC. So for this, it is showing this sort of response, and it is taking much more time to reach up to final value. Okay. Now these values, how I have selected these values, that I will tell you later on. Okay. So this is critically damped response. In critically damped response, case 2, that is R by 2L whole square is equal to 1 over LC. If this is the case, then the value of voltage or the steady state will be reached earlier than that of the previous. You can see here very sluggish response is there. It is taking large amount of time to reach to the final value, whereas this is somewhat faster than that, which is achieving the final value in less amount of time. That is the critically damped system. And the values, how I have selected all these, that I will let you know in very small amount of time. And this is underdamped response, where R by 2L whole square, it is less than 1 over LC. Then these are the values, and such oscillations will take place. So this type of oscillatory response, and after certain amount of time, it will reach to its steady state value. So such responses are there. So this circuit, RLC circuit, I have simulated for you, and this is the website where I have stored that circuit, http:// and this is the address. So you can copy this and put it in your browser window, so that you will be able to observe the same circuit which I have already stored it for you. Now I'll change the screen. I'll stop sharing the screen, and I'll share the screen of the practical. Yes. So is it visible to you? I have changed the screen. Avi?
Yes, sir.
Okay, fine. So this is the RLC circuit. This is the value of R. I'll take this spotlight. Okay. This is the value of R, 9 ohm, this C, 2 millifarad, and this 5 Henry. This is the RLC circuit. Now, this switch was open for a long time. So you can see, you can observe in yellow spots, you can observe the current. So current waveform is shown in yellow dots, and this is the screen of oscilloscope on which you can observe now. It is the totally relaxed system. So initially relaxed system means there is no current flowing in the circuit, there are no voltages stored across any capacitor, inductor, or no energy stored across inductor. So that means voltages and currents are at zero level, and it is shown on this oscilloscope screen. Okay. Now let us begin the discussion, and these values I have set it for the critically underdamped system. So in case of underdamped system, what is the condition? Condition is this R by 2L whole square, that must be less than 1 over LC. So what is the value of 1 over LC? It is coming out as L value is 5 Henry and C value is 2 millifarad. So 1 upon 5 into 2 into 10 raised to minus 3, it is coming out as 100. Whereas R upon 2L whole square, that is 9 upon 2 into 5 whole square, it is coming out as 0.81. So 0.81 is far less than 100. So that means the system will behave as if it is a underdamped system. Now let us observe it. I'll press this switch. So as soon as this switch is pressed, current will flow in the circuit, and now you can observe on this oscilloscope, the green waveform is of voltage and yellow waveform is of current. Now current flowing through the circuit as well as voltage across capacitor, initially both were 0, but as soon as we are pressing the switch, current will flow in the circuit, and that is of the order of the nature of oscillating. As the values of R, L and C we have set in such a way that the value of R by 2L whole square, it is far less than 1 over LC. That means the system will behave as if it is a oscillatory, or it is a underdamped system. Okay. So you can observe here, current was initially flowing in the circuit. It was of oscillatory nature, and these oscillations are of dying out nature. First oscillation is having highest peak, then the second, then the third, then fourth, and so on and so forth. You can observe in this yellow waveform, these oscillations are dying out, and at this, after this particular moment of time, it is gone to zero value. So current has gone to zero value. Now you can observe the same thing on this capacitor voltage waveform, which is shown by the green waveform. Initially it was 0, then it has raised to certain value, then which was more than the voltage V. Then again it has came down, again gone up, down, and these oscillations, after these oscillations, it has settled down at this particular time, which is equal to 5 times T, which we have already seen in the theory class. And now onwards, the voltage is settled at V, whereas current is settled at 0. So this is the steady state condition. And now in this circuit, you can observe that the current which is flowing through this RLC circuit, it has settled down and it is slowly coming to zero value. And if we'll wait for a certain amount of time, these spots will totally stop and the value will become equal to 0. Okay. Now, if I'll change the case, that is, this is the forced response. Now, if you want to see its source-free response, that means whenever this switch was connected, means this source was connected to this circuit for infinite amount of time, that is, the steady state has already achieved, that is, the voltage on this capacitor, it is equal to the supply voltage, and you can observe it on this screen that it is having the value, it has reached to the value of 5 volt or whatever the supply voltage you have applied, it has reached to that value, and the value of current, it is 0. You can observe here the yellow dots, they are totally stopped in this circuit. That means it is current is not flowing in the circuit. Only voltage available across this capacitor, it is equal to equal to maximum or 5 volt equal to the source voltage. Okay, and now if I open this switch, you will find that the voltage on this capacitor, it has started reducing and current has started flowing in the circuit, and both are of oscillatory nature. The voltage waveform from maximum volt or steady state value, it has started going down in oscillatory nature, whereas the current in yellow waveform you can see, it has also started oscillations, and both these will die out after certain amount of time. And we know that for a source free response, if we are removing the source for a long time, then the voltage as well as the current will, steady state values will be 0. That means in the circuit, there won't be any energy stored across any device, that is neither not device, components you can say, on capacitor also or inductor also. And you can observe here, both the values are gone to now 0. So this is for the underdamped system. Now let us change the values of these components so that it will become once overdamped and once critically damped. So let us go after this underdamped, we'll go for critically damped. For designing the value of critically damped, now we know that value of R by 2L whole square, that is R is 9, then 2 into L is 5 whole square. If you will find out, it is coming as 0.81. Now 1 over LC. If L value will keep it as it is 5 Henry and C value, let us say it is unknown. So 1 over L into C, that is 5 Henry into C, is equal to, if we'll put it as 0.81, which is equal to R by 2L whole square. So then we have assumed that R by 2L whole square is equal to 1 over LC, which is the condition of critically damped. And from this, you can find out the value of C. C will be 0.81 into 5. So it is coming out as 0.25. So if we'll put the value of C as 250 millifarad, I'll change this value to 250 millifarad, then, and if now this circuit has settled down, no current is flowing in this, no voltage on this, you can observe on the screen of CRO that there is no voltage, no current, 0 voltage and 0 current. Now let us put this switch on. As we are putting this switch on, this response is of critically damped system, and the response of critically damped system, as in theory we have seen that it will reach to the final value or steady state value after certain amount of time, which is definitely more than that of the underdamped system. In underdamped system, it will reach in the smallest amount of time. In critically damped system, it will reach to somewhat more amount of time than that of the underdamped system. Now you can see that in this there are no oscillations. The value of current or the nature of current you can see, it has gone up and then it has started reducing and it has gone to zero value. Whereas the voltage waveform you can see, which is in green, it has started from zero and it has reached to its maximum value after 5 times time constant, and then it will be maintained to its constant value. Okay, so this is the critically damped system. Now, if you want to design overdamped system, then for overdamped system, this ratio of 1 over LC, that should be very less than that of R by 2L whole square. Now R by 2L whole square, that value is 0.81. Let us take it as 0.4 for 1 over LC. L value will keep as same 5 Henry. So 1 over 5 into C will be equal to 0.4, let us say. So if you will calculate this from this, the value of C as C equal to 5 into 0.4. So it is coming out as, it is coming out as 2 millifarad. Sorry, 500 millifarad. Okay. So I'll make change of this. First I'll open this. I'll change this to capacitor value to 500 millifarad. So if I'll make it as 500 millifarad and then I'll put this switch on, let us observe what will be the nature of response. So nature of response will be of overdamped system. So overdamped system means it will take some more amount of time to reach to its final value than that of the critically damped. Okay. So you can observe here, we have started it at this particular instant. That's why current has started increasing and then again it has started reducing. We have not allowed the system to totally relax. That's why this some transition you are observing. So you can repeat the practical. While repeating the practical, you allow the system to settle down. So that means whenever the current flowing through this particular circuit will become equal to 0. That is, whenever these yellow dots will totally stop, then only you try to change the position of this switch. Either you switch it on or off. Okay, then you will find it. Clearly you can observe the changes in the response. Okay, so now you can observe here, this is the critically damped response. You can find this was the very small time, whereas you can observe it, this is the large amount of time for taking, which is taking to reach up to the steady state value. Okay, so I hope you have understood this practical.